So, in the first module, now we have the overall different types of the manufacturing process we have already discussed, their properties, what type of properties all we have discussed. Now, we will try to look into that. The next component of this module is the physics based modeling approach at the different scale. Here I will try to explain the different approaches, and I am more focused on the physics based approaches and the construction of a particular model. What are the different components we need to understand before developing of a mathematical model. So, to start with that, we can look into that what are the approaches. Normally, if you try to make some physics based modeling approach, and of course, this general purpose of to develop a physical system, but first thing is that what are the physical system represents. We represent the domain, we first fix a domain of the analysis. So, this is the solution domain, and we try to look into, once we fix the domain, within this domain what are the physical phenomena is happening with this domain, and what way we can represent all the physical phenomena within this domain, and of course, what way we represent the in the mathematical sense. So, normally the representation or general format to represent a particular physical system, the first is the one way is the equilibrium system. The system is in equilibrium conditions, we normally assume that equilibrium condition, and once it is the equilibrium conditions, then we try to look into the what are the governing equations normally acting on this particular process. So, for example, if it is a static system, and we can say most of the cases we assume the heat conduction equation is prevail. So, three dimensional heat conduction equation is the standard equation, and that we assume it is a under equilibrium condition, this equation is satisfied, and once we know the heat conduction equation with this domain, we just solve this governing equation and we can get the solution in the form of the temperature. Of course, rather the heat conduction equation, I can say that better to represent in terms of the energy equation. So, from the energy equation we can solve the temperature distribution, for example. That if we look into the momentum equation, that is valid within this solution domain, and from the momentum equation, if we solve in case of fluid flow analysis, we can get the velocity field is as the output within this domain. Of course, this is the one system, or the system may be dynamic system also, and of course, this dynamic system must analyze the what are the kinematical behavior also within this dynamic system, and this dynamic system can be represented in terms of governing equations. So, once we represent a particular system in terms of the governing equations, then we try to find out the solution of this equation. So, once we get the solution of the equation, we can get the distribution of this variable. So, this governing equation can be solved numerically, can be solved analytically, but when there is no solution of the analytical solution because of the complexity of the problem, we can go for the numerical solution. And of course, once we look into this form of the governing equation, either equilibrium system or dynamic system to represent in the form of a governing equation, then to represent certain phenomena, are we using this governing equation, in some part there may be the possibility of using the constitutive equation relation, constitutive equation or constitutive relation. But of course, along with the natural and boundary condition, that is also part of the system, because the governing equation is valid within this, but boundary interaction is also important to specify, and that boundary interaction, spatial boundary interaction may be possible, but the boundary interaction in the form of a as a function of the time, that is also possible, but that normally we do in case of transient problem. We need the time dependent boundary condition that can be represented in terms of the initial condition or other kind of boundary condition. But if it is a, we assume it is a steady state situation, that means the all equation is happening within the system under steady state condition, that means is independent of the time, then spatial boundary condition must be defined to get the solution of a particular system of the equation. Now, I am talking about this thing apart from this equilibrium system and dynamic system representation, there is a role of some constitutive equation also. Then constitutive equation actually relates to different physical quantities between two quantities. It is a what way this physical quantity relates. For example, constitutive relationship between stress and strain. What way I can relate between the stress and strain, in that way you can form the constitutive relation. So, these two physical quantities. So, therefore, it does not directly, not necessary is always to try to follow the physical law, rather it can be combined with other equations, such as this quantitative equation can be used in combining with other equations, for example, the equilibrium equation or kinematical equation, which do represent the physical laws. Actually, by representing the equilibrium equation or kinematical equation, that actually represents the physical law, but constitutive equation may not follow the physical law. But what we can form the constitutive equation? We can get some example to form the constitutive equation. So, the constitutive law parameter in this equation can be derived from the experimental observation. That constitutive law, with the help of the experimental observation, we can relate between the two physical quantity to make some constitutive relation, and that is often called the phenomenological modeling approach. So, phenomenological modeling approach means we normally observe through the experiments what the phenomenological things happening during this process, and there from this through large number of experiments normally we try to relate between the two physical quantity, and that is normally called the constitutive relation between this. But this constitutive relation can be linked with the physical law, but physical law is normally represented by the in a dynamic or equilibrium system. So, that under the equilibrium system we can link with the constitutive relation, and we can further solve the different kind of the problem. So, therefore, constitutive law parameter can be derived from the experimental observation, and it is called phenomenological modeling, but the methodology is to explicitly include the variables from the physics as the internal state variable. For example, when you try to explain that phenomenological modeling, say recrystallization modeling, for example, recrystallization modeling, and which is associated to metal deformation process. So, when you deform a particular component in material deformation process, in metal forming processes, that we represent the deformation process as a function of strain rate, or as a function of strain, and or as a function of temperature. Now, all these three are variables here. Now, the internal state variable can be represented in this process when you represents that recrystallization mechanism. That internal variable can be the dislocation density. Now, during the deformation process, how dislocation density evolves, that can be linked with the parameter in terms of the strain, in terms of the strain rate, or as a function of temperature. But the internal variable in this case is the dislocation density. Now, we try to look into that based on this dislocation density, considering as a internal variable during the recrystallization process, and we can predict what is the average recrystallized grain size after the deformation process once finished, or at a particular state what are the amount of the stress generate through the recrystallization process. So, this way we can develop one particular model, but when you phenomenological model, we try to represent all these things, it is in terms of some internal variable, internal state variable we try to represent. Of course, this state variable can be included in the recrystallization model as a grain size also. Average grain size can be a state variable as well. So, therefore, other possibility to determine the format of a constitutive equation based on the knowledge about the physical mechanism and causing the deformation. If you identify that what are the physical mechanism responsible for the deformation process, and that physical mechanism can be represented in terms of some other parameter, one parameter in the form of one parameter, and that parameter can be included in this for the development of the constitutive model. So, therefore, an alternate to the phenomenological modeling is to derive the constitutive equation from the low scale. Of course, in the phenomenological modeling we try to derive some physical mechanism is responsible here, that can be derived from the very low scale. Where the low scale physics is basically we can rely on the low scale physics, because the low scale laws, the laws of the physics is well understood at very low scale. So, we can take the information from the low scale, and then we can decide the constitutive equation by the information from the low scale mechanism. For example, parameters for the grain size methods. So, therefore, parameters for the grain size method for we look into the microstructural evolution, and we can evaluate what is the parameters, and that actually responsible to predict the grain size. That is the one example, just by looking to decide the parameters at the low scale. Now we can give the another example. For example, determine the material properties Young's modulus. We know the Young's modulus we can easily measure in a particular material through experiments just by looking into the universal tensile testing machine for a particular material, and therefore, that value Young's modulus can be used some mathematical model in the continuum model. We want try to develop the stress analysis for elastic stress analysis for a particular material. Then when you try to look into the elastic stress analysis, in that case there is a requirement of the Young's modulus for a particular for this particular material. So, therefore, using this value that from the experimental measurement and give the input property to the model, and then model can predict the output in terms of the material response. So, of course, Young's modulus once we measure that from the universal tensile testing machine for a tensile specimen, that information is actually usable at the continuum scale. That means, in the we cannot use this information probably in the very lower scale prediction. So, then in that cases we need to look, for example, we cannot use the this Young's modulus for a bulk of material what we exact from the universal tensile testing machine is not possible to use. When you try to predict the single crystal structure, what is the Young's modulus? So, that in that cases we need to refine the experimental procedure to find out the Young's modulus, and for this particular cases. And there is another difficulties also, because when you try to look into the lower scale, for example, in the single crystal structure, the atomic arrangement may be different in the different directions. So, therefore, that E value can be different direction. So, in that cases if we look into conduct the experiment at the different direction, so then we can get the inelastic behavior at the, that means different values of the E at the different direction. But if you when you do the at the macro scale experiment to do the find out the tensile specimen, the Young's modulus for tensile specimen, we apply one single direction, and in that direction that is the value of the Young's modulus, and we assume that most of the cases it is a homogeneous structure at the macroscopic scale, macroscopist point of view. So, therefore, if we change the scale, we need to refine the experiment to get the information. So, therefore, when you look into the continuum model, some information from the micromechanics models can be incorporated account and more detail from the material structure at the grain scale. At the grain scale, what are the material structure? We can develop them, look into the micromechanics available at the grain scale, and that information can be used, can be supplied to the model for the development model at the continuum scale or the micro scale. So, therefore, properties at the micro scale, but properties of you can get the just have given example, the if you measure the Young's modulus in a 110 direction for a single crystal structure and 111 direction and maybe other direction and 110 direction, then in that cases we will get the huge variation of the Young's modulus is possible, because crystal structure are different. So, therefore, what this variability normally we can do the averaging out, and we can give the average Young's modulus to the next scale to find out to develop a particular model. So, that means that is called the lower scale we average and pass the value to the continuum model, and that is normally done through the homogenization theory. So, I am not going into that what theory can be in details about this theory. So, therefore, micromechanics model or micromechanical model can provide some local variation and that of the behavior, and then we can pass the local variation in the average form to the continuum model for development of the next scale model in the larger scale model. So, now we can look into when you try to link the one scale to other scale, and then people have developed that multi-scale modeling in the length and time scale also, both multi-scale modeling is possible. So, now people are working in this different scale modeling approaches. So, normally 4 length scale in multi-scale materials modeling normally happens. One is the electronic structure, we can look in the very lower scale understanding and prediction, then atomistic scale, then we look into the microstructure, finite element method can be used, but atomistic scale we can use some molecular dynamics or some statistical physics also we can use to make the model at this scale. And finally, we normally use for example, we say we are using the governing heat conduction equation and we are solving, that is actually we are doing in case of in that scale, continuum scale. So, therefore, there are 4 hierarchy level of the modeling different scale modeling approach. So, length scale we can see the length scale is 10 to the power 7, that means 10 to the power 7 minus 10 equal to 10 to the power minus 3 in that scale. So, that means millimeter scale we can get the continuum model. And of course, this continuum model we can use the CFD method, computational fluid dynamics, even we can use finite element method also, these numerical techniques we can use to develop model at the continuum scale. Now, importance of the multi-scale methods. Now, limitation of the industrial simulation today is the continuum models are good, but not always adequate, because for example, problems in the fracture and failure of the solids require the improved constitutive models, because when you try to predict the fracture failure, it is very difficult to represent this thing using some kind of Gomin equation there. Rather, it depends more on the some constitutive equation, but it is a best if you analyze the fracture and failure mode from the continuum scale or micro scale approach, then it is very difficult to predict this behavior. So, therefore, in this case there is a requirement of the to look back to the lower scale model to predict the fracture behavior of a particular material. So, therefore, macroscopic material properties of the new materials, this is another composites which are not readily available while they are not needed in the simulation when you try to look into simulation based design. So, composite material is very in that cases probably we can get the material properties by analyzing at the lower scale. Therefore, detailed atomistic information is required in regions of the high deformation of the discontinuity. So, when try to predict the discontinuity deformation behavior. So, in that cases it is better go for the we can predict the material behavior just looking look back to the lower scale approach. Similarly, molecular dynamic simulation also done nowadays in the in that scale the limited to the small dimension, that means 10 to the power 6 to 10 to the power 8 atoms. So, we know that the size of radius of atom is less than a nanometer. Therefore, in that scale the domain is very small, and that is time frame. Of course, the time scale also when you try to molecular dynamic simulation, the time scale also lower scale, time scale is in the nanosecond level. So, that nanosecond level time scale and the domain is in that 10 to the power 6 to 10 to the power 8 atoms, the smaller domain. So, that in that domain if you do the simulation process, so that simulation result directly we cannot use to the continuum model. So, therefore, that information may be necessary to develop model in the next scale, say maybe in the mesoscale model, the information or atomistic scale model we can get we can give this input and can develop the model. And of course, experiments, even the analysis molecular dynamics exist in the very small time scale in the nanosecond level, but when you try to do the actual experiment of a nanosystem, it is not exactly much longer time is required actually to conduct the experiment. That means, nanosecond phenomena, not necessary the nanosecond phenomena, the experiments can be conducted within the time frame. So, time frame can be much more. So, these are the typical issues associated with the different type of the multi-scale methods, but most important of the multi-scale method is that how to link one scale to another scale. So, therefore, two approaches we follow in multi-scale modeling approach. One is the hierarchical approach. So, hierarchical approach means known information at one scale and to generate the model for the larger scale. Therefore, information passing typically to the some sort of averaging process. Therefore, at the lower scale we make the properties, we make the information, get the information lower scale output from the model, and then we averaging out the properties and then it pass to the next scale. So, that is the typical approach in hierarchical approach. For example, in that cases bonding models, potential and constitutive laws can be developed just by looking into the model into the lower scale. Concurrent approach is the perform simulations at different length scales simultaneously. So, therefore, at a time at the different length scale we perform the simulation, and but difficulty is the how to link, how to get the performance from one information from one scale to another scale. So, therefore, relationship between the length scale in this case is mostly are dynamic in nature. So, the pass the information in this one scale to another scale is the major issue in case of the concurrent approach. Now, multiscale modeling model, if we look into the continuum methods, because most of the cases we use these continuum methods, and of course, the method modeling of manufacturing process mostly based on these continuum methods. That means just finding out the equilibrium equation and try to solve the equilibrium equation to get the output variable. So, therefore, continuum methods we try to look into the assume the continuous media basically and treat the properties of the system at the field quantities. So, properties of the system at the field quantities, and therefore, numerically solve the balance equation or coupled equation we can solve. For example, thermal and mechanical analysis, we can couple it and then we can solve this, we can get the output variable. And of course, coupled with the some phenomenological equation can also be used here, and of course, along with the Gauss equation some constitutive relation can also be used. For example, thermomechanical analysis, thermal analysis can be based on the Gauss equation, but when you look into the mechanical analysis, it is mostly developed based on the constitutive relation. So, therefore, and if we incorporate the some lower scale the prediction of the certain variable, and for example, predict the failure behavior, then in that cases if you want to predict the failure behavior in from the thermomechanical analysis, then we need to incorporate some kind of the phenomenological modeling approach there by introducing some sort of state variable there. Now, the advantage disadvantage of these things, and of course, continuum model can, in principle it can handle the system of any, even for macroscopic scale also size can also be handled by using this continuum model, and of course, it is in the continuum model can also handle the dynamic processes also, and that dynamic processes may exist over a time scale. For example, atomistic model or in that molecular dynamics model, in that cases the time scale is very low. So, that valid the relation statistical valid over a very small time scale, but this continuum model is another sense, it can be valid for a longer time scale. That is the main advantage of continuum models. And but required input, for example, diffusion coefficients, some elastic properties of a material, and particular equation of a state from experiment, that is the input to the model. So, therefore, when you define some material properties, and that material properties normally evaluate from the experiments, and we give the inputs to the experiments, we give the inputs to the input to the model. That is one approach, or these properties can be evaluated just by looking back to the lower scale methods. So, from the lower scale methods we can predict the properties, and that can be given to the this method, but lower scale that can be difficult to obtain, because in that cases we need to develop the model at the lower scale to predict the properties of a particular material. And of course, this continuum based method cannot explain the electronic and the molecular level in detail. So, this not getting no information, nothing prediction at the what is happening at the molecular structure detail of a particular material. So, that information we cannot get from the continuum methods. Now, connection, how we can connect the different scale, that is the one is the upscaling of method. That for example, upscaling means that using results from a lower scale calculation. So, we can use the results from the lower scale calculations to obtain the parameters for a higher scale method. So, therefore, first we use the lower scale calculation and we get the parameters, and we use this for the higher scale method. This is relatively easy to do, and of course, this is called the deductive approach, and in this upscaling method relatively easier, because we get the information in details in the lower scale, and that predict the properties, we average out the properties, and that properties can give to the next scale. So, from lower scale to the higher scale, it is easy to move from this upscaling method. Again example, for example, calculation of the phenomenological coefficients. For example, the elastic tensor, viscosities, diffusivities, all these coefficients or for this particular properties, then that can be done from the atomistic simulation. From the atomistic simulation can be done for later use in a continuum model. So, that we can give the upscaling one example. The upscaling is that phenomenological coefficients, maybe when you try to predict the elastic tensor, which may be associated some kind of the coefficient, viscosities, that properties, or diffusivities properties, and diffusivity sometimes we represent in terms of the some coefficients also introduced. So, that values or values of all these parameters that can be evaluated from the atomistic model, atomistic simulation model, and that model can be stored, and that data can be used for the continuum. This is the one approach, or this is the one advantage of the upscaling of the upscaling during the multiscale modeling approach. Now, it can be downscaling approach can also be possible in the multiscale model. So, then in these cases higher scale information. So, in this cases higher scale information passed to the lower scale information. So, that is higher scale information normally we can observe from the experiment, open experimental. So, that means it is easy to obtain the to conduct the experiment at the higher scale. For example, if you look into the macroscopic scale, in the macroscopic scale we can obtain the experimental results, and that information can be passed to the to build the develop or the lower scale. So, here is the only advantage is the doing the, because we have the scope to easily do the experiments, and that information can pass from the higher scale to the to develop the model at the lower scale, to build the parameters for the lower scale. But this is more difficult as compared to the upscaling due to the non-uniqueness of the problem. So, non-uniqueness of the problem, because if there is a uniqueness in the problem, in the sense that if you want to develop the fracture model, and by looking into the information from the higher scale data, basically that if you correlate the fracture module in the responsible parameter for the fracture of a particular material. So, then that correlation can done of the continuum scale or the macro scale modeling approach, but this information is cannot be used for the to develop the model for the lower scale, because the fracture normally happens at the in the sometimes is kind of catastrophic failure may happen during the application of the fatigue loading in a material deformation process. So, therefore, for example, the results from the mesoscale simulation do not contain the atomistic detail. Definitely mesoscale model do not contain the atomistic detail, but it is would be desirable to be able to use such result to rerun the atomistic simulation level. So, inductive approach, that means we can compare the results by some assumptions, and this inductive approach may not be very convincing to develop the downscaling modeling approach. For example, we can give an example also, the stress strain curve for a randomly oriented polycrystal. So, I can easily predict the randomly oriented polycrystal can be used to predict the shear stress shear strain curve for a single crystal. So, we can use this relation, for example, the strain and this stress, the stress and stress for the polycrystalline material, we can easily find out this stress versus strain graph for a polycrystalline material. But if we know the but this polycrystalline information from the stress strain diagram polycrystalline material, that information can be used to predict the at the lower scale. That means for lower scale in the sense that for single crystal structure, the variable is the shear stress, and shear strain is more important in the single crystal structure, because the normally slip happens due to the application of the shear stress there, and critical shear stresses may be responsible there. So, therefore, shear stress and shear strain diagram is more important in case of the single crystal structure to predict the failure behavior of the single crystal structure or yielding behavior of a single crystal structure. Now, here this conversation is possible by using some Taylor factor, but this Taylor factor it is a average value of the Taylor factor. So, basically the local behavior by passing the information from higher scale to the lower scale, we can we are not we basically we are suppressing the behavior at the local scale, rather we can passing the only the averaging value from higher scale to the lower scale, and this to some extent can be represented by this. This is suppose stress strain is something like that, and if a single crystal structure it is a strain and it is a shear strain, it can be something like that, just to maintain the average value of the Taylor factor, and that Taylor factor, average value of the Taylor factor actually comes from the types of the grain distribution basically in a polycrystalline material. So, this Taylor factor can be estimated for a randomly oriented polycrystalline. So, here the downscaling of the modeling approach is little bit it is not very much convincing for downscaling approach as compared to the upscaling approach. So, normally in the simulation process mostly we follow in the upscaling approach in case of multi-scale model. Here you can see that multi-scale modeling of the materials, the understand the molecular level of the origin of the materials behavior, we can see that also, and predict the behavior of materials from the first principle. So, we can use the basic law and we can link from the one scale to another scale. Here you can see the quantum mechanics is responsible in the nanometer scale, and of course, within the femtosecond, picosecond and nanosecond, in that time scale this model is valid. When you go for molecular dynamics, it can go little bit the nanometer and micrometer range, and then scale is little bit, time scale is little bit increasing here. Then once from molecular dynamics to it can be reach link with the mesoscale model development. So, model development, or we can say the grain scale model development, and then that time scale also increasing here, and finally from mesoscale to we can reach the macro scale model. So, this macro scale model we can see is a little bit higher time scale and length scale also in terms of the meter within the millimeter to meter in that range. So, therefore, with this level of linking in the multi-scale modeling approach is the main the different process methodology has been developed, that how we can get the information from the lower pass the information from lower scale to higher scale. But when we pass the information from lower scale to higher scale, mostly in the averaging, by averaging the properties. So, then the average value we can pass from the mesoscale to micro scale, and based on that the different level of the scale has been developed, and each has we can analyze the different scale of the models, and we of course we can link the different scale of the models to finally predict this thing. So, but how it is significant, because when you try to develop some kind of the new material, so understanding of the different scale multi-scale modeling is to predict that expected behavior of particular material. So, then based on the multi-scale modeling approach is the most suitable modeling approach to predict the behavior of a new material when you try to develop on particular material and try to analyze their performance. So, therefore, we need to understand the link and the understanding the mechanical properties or other kind of properties at the different scale. So, but most of the cases we normally focus on this macro scale modeling approach, and we can do all the tensile testing, universal tensile testing or hardness measurement, all kind of information normally we do for the development of the macroscopic element. And here we supply in macro scale only product, here we supply all the material properties, but that material properties are normally evaluated in case of at the macro scale. But in general, what are the challenges in multi-scale modeling? We can point to as we can say that of course, if we lower down the scale, then for large number of degrees of freedom, large number of variables actually involved at the atomic scale, where if you go to the higher scale, the degrees of freedom gradually decreases. Other difficulties in multi-scale modeling is the interfaces, basically how to represent the interfaces and mismatch of the dynamic properties, because interfaces actually act through dynamic behavior. So, therefore, it is often quite possible to mismatch of the dynamic properties at the interfaces. That is the one difficulty in the multi-scale modeling approach, and of course, we try to link at the different scale. So, analysis can be done at the different scale. So, therefore, for example, if we try to analyze for example, laser welding processes and this thing. So, laser welding processes, this laser welding processes we can in the if it is a pulse laser welding process. So, we can analyze the pulse laser welding process, maybe time period, if it is a pulse duration maybe or the order of the microsecond. Then in the time scale in the microsecond, in that time scale we can analyze this process. But for example, if we try to analyze the ultra short pulse laser welding process, then ultra short pulse, the pulse duration may be in the of the order of femtosecond, picosecond. So, therefore, we need to bring the analysis in the reduce the time scale in that second, and this analysis So once we change time scale, so analysis procedure can be different. So therefore, for example, this ultra short pulse laser welding process, we cannot apply simply the heat conduction equation, Fourier's law of heat conduction. So we have to analyze in the different scale. So that's why there is a different multiple time scale, the analysis behavior will be different, and of course the interdisciplinary nature of the multi-scale methods, continuum mechanics, therefore classical particle dynamics and the lattice mechanics, these are the all mechanism are different, we need to understand all these mechanisms. So we have to link this mechanism, the quantum mechanics also, quantum chemistry, thermodynamics and statistical physics. So analysis of all this is required to develop a model and to understand this model to develop the interdisciplinary nature of multi-scale model. So getting knowledge of all these things is sometimes difficult. Then if you look into the atomic scale plasticity, then we have to look into that lattice dislocation behavior. So we have to analyze the all this matter and different things at the if there is a scale are different. So analysis procedure modeling approach will be all are different. And finally, the algorithm issues in large scale coupled simulation. When you couple one scale to another scale, how to develop the algorithm, that is one issue. Maybe in the different time scale couple or in the same time scale the different analysis behavior, for example thermal and mechanical analysis or thermal and fluid analysis. So how you can coupling this thermal analysis and the fluid analysis, because some parameters of variable is a common variable between these two analysis procedures. So therefore developing of the algorithm and for the large scale simulation is the another difficulty of the in case of multi-scale modeling approach. I can give an example also. For example, computing the response of a single crystal structure. How we can do these things, what are the input are required. If you see the input slip system, we should know for a particular metal what are the slip systems, then what is the initial crystal orientation and what are the material parameters is involved these things, and then we should know deformation rate at each crystal, what are the deformation rate, and of course some constitutive equations also is involved, get input what are the kinetics, following the kinetics, elasticity, elastic behavior, how it is following, plasticity behavior, how you are predicting the representing the plastic behavior single crystal structure, and then even plastic behavior depends on the flow rule, and then orientation evaluation, of course it depends on the hardening rule. So all information gave to this thing, and then it creates the single crystal constitutive model looking into all this type of equation input and out these input parameters. Then we develop the single crystal constitutive model, then we predict the crystal stress and crystal orientation, and then slip system hardness, and then finally crystal stiffness. These are the output from all this input. So once we taking the input following the different constitutive equations, we can develop the constitutive model single crystal structure. We can get the output in the different crystal structure, crystal orientation, but all this is a particular scale we follow. So all this phenomena happening at a particular scale, particular time scale. Then we can give another example. For example, if you want to develop the constitutive model for single crystal structure, then normally we see what we happen, the Schmidt's law predicts the elastic perfectly plastic. So the deformation happens during the slip system, slip occurs within the single crystal structure. It's a is that it's a just elastic component, and just from elastic to perfectly this kind of metal behavior normally follow in case of a single crystal deformation process. So yield will begin on the slip system when it just cross the critical value of the shear stress, and that shear stress, critical value of the shear stress is independent of the tensile stress or any other normal stress on the lattice plane. If you know this is the yielding behavior of a particular single crystal structure, then you try to develop the model for the deformation behavior of the single crystal structure. So therefore we see the elastic perfectly plastic behavior, but in that cases that the transition from elastic to plastic can be smooth also. So when you looking into the smooth transition from elastic to plastic behavior, then we can look into the power law behavior. We can represent this power law equation, the smooth transition from elastic to plastic. Of course in that cases other parameter also can influence, that is the shear strain rate. So strain rate also in slip system is estimated by the constitutive relation, that can also be estimated from the constitutive relation. But of course kinematics of the plastic flow can be represented by the rate sensitive or rate insensitive, or we can avoid the non-uniqueness of the set of the active slip system typically present in the rate insensitive model. So, therefore, we have to look into the uniqueness of the active slip system, because one particular single crystal structure there are so many slip systems, and that all the slip systems may or may not active at a time. For example, in FCC crystal structure there are 12 type of the different slip systems may happen. So, therefore, 12 slip systems may not active at a particular time. So, therefore, we have to look into that how many slip systems is minimum slip systems is required to activate the deformation process. So, all this matters when you try to develop the constitutive model for single crystal structure. So, therefore, all this analysis is actually required or information is required. Now, from this different modeling approach at different scale, we can make some conclusion also that concurrent scale coupling. So, concurrent scale coupling techniques have been evolved significantly in the recent decades. So, people have tried to look into that concurrent scale coupling techniques for the development of the multi-scale model, but most robust and the stable methods become available applicable to an increasingly wide range of the problems. So, that I think now it is available, the most robust and stable methods becomes available, but we need say separate study on that to utilize the different multi-scale modeling approach. Then concurrent multi-scale methods are readily available, and simulation codes can be downloaded from the website also. This website we can get lots of this thing the concurrent multi-scale approach or model we can get from here also. And some researchers think that concurrent coupling is difficult and associated with many numerical and physical difficulties to implement all these things. Therefore, they favor the hierarchical methods as a more cleaner way to convey the information across the scale. So, these are the typical I think conclusion for the development of the multi-scale model. But of course, to understand the multi-scale model, we need to understand the physical mechanism behavior happenings at the different scale. This is the first step, and second step is the how we can link all these scales, and of course, when you linking all these scales, what may be the algorithm we need to follow or any algorithm we need to develop to get prediction of a particular behavior. And of course, this multi-scale understanding all this multi-scale modeling approach is maybe more suitable when you try to develop some new materials, or maybe for a particular materials we try to develop some good we try to propose certain manufacturing processes. Therefore, all this approach is required in that cases. So, thank you very much for your kind attention.